because now what I can do is just deploy my eBPF agent on the nodes that are running my applications. No changes, no integration of an SDK, no manual probes or anything that are necessary. I have my entire application instrumented, producing metrics, producing traces for every single function.
Welcome to the podcast dedicated to the art and science of observability. This is Signal Over Noise. Hi, everyone, and welcome back to another episode of Signal Over Noise. So in today's episode, we are going to be talking about eBPF. Now, eBPF has become the clear favorite for high-scale performance-critical networks. And joining me for today's episode is Sven Cowart, the co-founder and CTO of ElastiFlow. And Sven is going to help break down why eBPF is our choice for kernel-level insights without the performance overhead or the application-level instrumentation. Welcome, Sven.
Awesome. Happy to be here. I love eBPF. I love talking about it. I like working on it. So thanks for having me.
Awesome. It looks like you got the outfit memo, black shirt and jeans. So
absolutely.
I know it's kind of
black jeans too. So
perfect. I love it. Awesome. So before we get into today's topic of eBPF, maybe let's rewind the clocks a bit and take a look at what life was like before eBPF. Can you give us a little bit of history and some of the pain points that we were facing before that led us to where we are today?
Absolutely. Let me give a quick shout out to the documentary eBPF Unlocking the Kernel. It was created by Speakeasy Productions, and you can watch it on YouTube. It's a excellent visual primer for how eBPF came to be. That will do a much better job explaining the history than I will. But the problem really started with the fact that the Linux kernel is very slow to adopt change for a very good reason, because the Linux kernel is the bridge between the hardware and software on any server or computer that's running, and is the thing that's responsible for moving data across the OSI layers. And so any change to it can be, especially breaking changes, can open up security vulnerabilities and cause problems downstream from all the various distros that are developed on top of the Linux kernel. And so very rarely do you see breaking changes to the Linux kernel. And people had this idea that, okay, if I could just access the data in an earlier layer of the OSI stack, then we could avoid having to copy that data out of kernel space and into user space. They wanted a way to make the kernel layer programmable so that you could build applications on top of the kernel layer that has access in a safe way, in a privileged way, to the data in the kernel without requiring kernel changes. And that's where eBPF came from. Because and part of the problem was, right, is like if you really want that data as early as possible, and you don't want to need to copy it, because when you do, you assume that CPU overhead of actually doing the work of copying the bytes from kernel space to user space and then using it in your application. And that's how a lot of things like TCP dump, which is a very popular tool everyone I'm sure that's listening has used, that's how they work. But for applications that are designed to work in large scale environments, that's just not an acceptable solution. And so that's where this desire, I think, kind of came from, is that, and then what's been really cool is to see is how people have imagined different use cases for eBPF and then contributed different program types, which are, you'll hear me reference those and I'll explain a little bit later what those are, but to the eBPF virtual machine that runs within Linux. But all this kind of started in 2014 when eBPF introduced the general virtual machine and stateful maps into the Linux kernel. And all of a sudden you could run safe sandbox programs inside the kernel that could easily share data with user space without constant copying of that data. And that's huge.
Yeah, all that flexibility that brings.
Yeah, absolutely. And so at that time, what they did is introduce a few program types. Think of these program types as various hooks into the kernel. As data moves through the OSI stack, you could say something like now you can say something like XDP. I want to create an XDP program type. And what that means is at that hook, I'm actually getting the buffer that is connected and populated directly by the network interface driver, or the network interface. So now all of a sudden I have access to that directly without having to copy anything to user space, which is a really powerful concept. Alongside that, what they introduced was, they call them maps. And what that allows you to do is share data between kernel space to user space and backwards as well. So if I want to, for example, notify user space of saying, hey, I got a new packet and I parsed it for you, here you go, I could do that using stateful maps, or I could just put whatever parsed data I got out of that packet onto a map, and then the user space can grab it, and the user space can even update it and then share data with my eBPF, or the kernel space program part of my eBPF program, that of information that it needs, like certain configuration variables or something like that. So then 2016 came along and Cilium launched, which I'm sure most of you have heard of if you've been in the APM space. There's a company called Isovalent, I believe recently acquired by Cisco, very big acquisition. They are the ones who introduced XDP. So that's that hook that lets you watch network packets within your kernel space program. And that opened up a whole set of awesome and useful applications for eBPF programs, specifically for networking. And I'll get into some of those things later. And then the additionally, shortly after, I don't remember the exact year, I think I want to say 2017 or 18, it's an acronym called CORE, and it stands for Compile Once, Run Anywhere. And then BTF, which stands for BPF type format. All these things have an insane amount of acronyms, so you have to bear with me.
Of course, we love our alphabet soup here.
Yeah. So those were introduced shortly after the introduction of XDP by Cilium, and they are very important contributions, because what it allowed eBPF programs to do was to say, I'm going to compile this eBPF program once, and it doesn't matter what version of Linux I'm running, it's going to work. It's going to work with any kernel. And that's huge, because before that, what it meant is that you'd have to, for every version of Linux, compile and distribute a eBPF program for every version that you also publish. So, right, it's just like version explosion of what you need to do and support. And that was very challenging.
Yeah, so much to maintain there.
Yeah. So Core really is, I think, the thing that enabled mass development of eBPF programs, and so that we didn't have to worry about that specific overhead, because before that, it was really like a tool that someone could use in their well-defined environment to write code for themselves that that they don't need to distribute with other users or customers or anything like that. Now, it doesn't matter if I'm running Ubuntu 20, 22, 24, Red Hat, doesn't matter anymore. Fedora, I could just run this eBPF program. It's going to run. And there are some caveats to that. For those of you who've programmed and built eBPF programs, you know that that's not entirely true, because earlier versions of the Linux kernel, especially like pre-4.12, there was significantly less instruction counts, so you couldn't write as much code in your kernel space program, and the complexity of it had to be really small, otherwise it failed the verifier check and all those types of things. And don't call me out on that, I know that's there. But for the most part, 4.12 and later, you basically can run anywhere. So eBPF didn't just make things faster, it also made kernel-level programming portable and practical for the first time. And that's been really awesome to experience.
Making it so accessible like that. So can we unpack that a little bit further and compare that to something like maybe sidecars, for example, why it's, better, faster, stronger type of thing?
Yeah, absolutely. I think it's important to understand what time sidecar architectures really became prevalent and why. So Google developed Istio, which was the a service mesh solution for microservices, right? So before, and that was deployed 2017. So pre-2017, you had a lot of people were talking about monolithic to microservice applications. I remember the number of O'Reilly books purely dedicated to that topic was just outrageous at the time. I bought 12 just to make sure I didn't miss anything. I mean, this arbitrary number, probably not completely accurate, but it also is probably pretty close. It might have actually been more than that. but everyone was trying to understand how do we best deploy microservice architectures at scale. And the thing about it is that the microservices, they are obviously connected by communication. So the network becomes really important, and security between those microservices becomes really important. And so service meshes try to address the need for things like MTLS between microservices and applications, L7 routing, some observability, rate limiting, network policy enforcement. So saying this application can only talk to this application, right? And that's where Istio plus their Envoy proxy sidecar came about, which is it was a great piece of technology for the time it was in. The problem with it, though, is that what it means to deploy a sidecar is every application you run is deployed as a pod, and each one of those pods has another pod attached to it. That is the sidecar. That's what we call it, a sidecar. So if you have 1,000 pods, well, now you have 2,000 pods. So you just doubled your, I mean, it's not a one-to-one multiplication of, like, if my application is 200 megs and 2 CPUs, it's not going to be that same thing. It's whatever the sidecar needs. But regardless, now you've just doubled the number of pods and the amount of resources that you've had or are required to deploy onto. And that's real cost. And not just that, because there's a sidecar now that if application A is talking to application B, I have to talk through the sidecar. I can't just directly talk to the other application. And so I've introduced 2 hops on each side of the connection, and that's going to introduce latency. And I have a good example that I can kind of explain it in more layman's terms. Imagine you have an office building, and the office building is your Kubernetes cluster. And that office building has 1,000 employees on it. And in the sidecar model, and the employees are your applications. In the sidecar model, every single employee would have a personal assistant that's also their bodyguard. And so Bob wants to send a document to Mary. And so what Bob has to do, he has to hand it to his assistant. The assistant's going to scan it. Then it's going to walk down to Mary's assistant, and Mary's assistant's going to scan it and then hand it to Mary. So, right, very inefficient. And that process of handing it off is what increases latency. And the simple fact that, well, now you have to house another 1,000 employees and pay 1,000 employees of salary. That's the computational addition that you have to do to deploy a service mesh using sidecars. If we take eBPF to that example, basically what we're asking, or what we would do is, what we'd say is that the office building, instead of each employee having an assistant, you can fire all those assistants, which is really unfortunate for all those poor assistants. But you can fire all them, you save all that cost, and instead you deploy smart doors, smart hallways, and tubes that can send things between employees, and basically like teleportation devices between employees. And you pay for that. There's still obviously a cost to that, but it's significantly less because you only have to do it once. And maybe you have to do it per floor, right? If this is a multi-floor thing, you have to do it per floor, but the cost is significantly less. And then when Bob wants to give his document to Mary, it's instantly teleported. They don't need to know or understand the mechanism of communication. It was also scanned in that process automatically by the smart doors and hallways. You just remove all the latency.
I love that. So it removes the friction, removes that latency. Now, what are the trade-offs? Because so far it seems great. How does that impact visibility when you're comparing eBPF to sidecars, for example?
Oh, that's a good question. I'd actually say it increases it, because in the sidecars model, you only have access to layer 7 things. So there's things that in the lower layers you would just miss or not see, because they would have already been taken away or obfuscated by the kernel's layer, right? Like, for example, you would have no idea if you're doing network analytics on something or using eBPF to do network analytics. You couldn't do that with layer 7 to understand what tunnels were used or so on by this network packet, where you could do that in the eBPF space. So I can't really say there's a downside to it, which is why I think even Istio saw the writing on the wall, and they now have Istio ambient mode, where they converted much of what the Envoy proxy did and have their own, I think it's called Z tunnel, where they have an eBPF based agent that does much of the MTLS and routing and network policy enforcement within eBPF space, and also exposes that telemetry now in eBPF space instead of in their previous L7 Envoy proxy. The downside's not really there.
All right, so that's some great background context, not only the history, but, kind of that pro-cons list, which cons doesn't seem like there's really a whole lot there. Seems like the obvious choice. Let's maybe dig into some use cases to see what that looks like in action.
Absolutely. So the first use case really came about I shouldn't say first. The first largely applicable use case that was reusable across organization was really brought about by Cilium with what they did with replacing kube-proxy with an eBPF agent, and they developed their own CNI to plug into any Kubernetes cluster. And what that did is allowed you to remove kube-proxy as the load balancer inside your Kubernetes cluster. So all that same latency and additional resource requirements that we talked about with sidecars is just gone because of Cilium. And from that, they were able to reduce the resources required to run large-scale Kubernetes clusters and make it more secure, because now you can do network policy enforcement in kernel space. The other thing that's really great about that type of development is you can do things like absorb DDoS attacks for the large part, because when you get a packet and you recognize the packet either violates your network policy, or you have something else detecting that this is anomalous traffic or related to some type of DDoS activity, you can just drop it right there and then. It doesn't actually propagate through the network and doesn't ever make it to your layer 7 applications, which is great. So your applications don't see any of that traffic. So that was really cool. So there's a bunch of things you can do around load balancing and network security that are really important and awesome. Another one of those projects is Falco. So they focus on generating alerts for the activities that you see inside your Kubernetes clusters. Those alerts can be network related, they could be file system related, and they can do things like detect suspicious activity related to DNS tunneling or DNS flooding, port scans, unsuspected file access, and they can do all that in real time thanks to eBPF and directly in the kernel, and then users of Falco are just notified of those events. And it's actually interesting. Falco is like, since some of our audience, I'm sure, is network engineers, and you might be familiar with Suricata. Falco is basically a Suricata for cloud native environments. So
interesting.
Pretty interesting, but it's like a rule-based engine. So you define the rules, right? And those are then passed from user space to eBPF space, and then eBPF space enforces all those rules. So really cool stuff that they've done there. And the other one, the last one, which for us as an observability company, the most important is the impact it's had on how we can collect telemetry and produce telemetry for applications. Before eBPF, if you wanted to instrument an application, you had to manually do it. So what that meant is you had to actually spend dev times planning, figuring out, okay, what are the metrics you want to collect about this? What are all the functions? Oh, I want to create a trace for this function. Now I need to instrument this function to have a trace in it. So it actually involved this back and forth between DevOps and software engineers to figure out, what do we actually want to see? What do we not want to see? This is all the stuff that's important to monitor. This is not what's important to monitor. And while that's still important to do, that part of the planning, we then had to spend dev time deploying that, or developing it, then deploying it, testing it, so on and so forth, which is really not great.
Yeah, that's probably not how they want to spend their time, right? Better.
Yeah, exactly. Like,
better ways to do that.
In an ideal world, we just want to deploy some magic box, and the magic box just instruments this thing, and that's what's called auto-instrumentation. And eBPF is what made, I think, that little buzzword auto-instrumentation become so popular, because now what I can do is just deploy my eBPF agent on the nodes that are running my applications. No changes, no integration of an SDK, no manual probes or anything that are necessary. And I have my entire application instrumented, producing metrics, producing traces for every single function. And that's just so awesome and a massive time save.
Yeah, absolutely. Helps you really almost ensure that you have that true full stack visibility without having to do that manual step.
Absolutely. And there's a great project called Obi now. It used to be Bela. It was donated by Grafana to OpenTelemetry and under the codename Obi, which stands for OpenTelemetry eBPF instrumentation. Another one of those acronyms. But I like it. I like Obi, a Star Wars fan. The Obi team has been talking internally about creating their mascot as like Obi-Wan Kenobi, which I would think is so awesome. We should definitely do that.
Also, my dog's name Obi after one, of course. So yeah.
That would be really great if that were to happen. But they're some of the people that made this possible. There's other tools that make this possible too, and we're one of them with what we do with Mermin, and that we really focus on a different part that wasn't being addressed by tools like Obi and others that are similar to Obi, which is instrumenting the network interface. And what that lets you really do is see fine grain, high cardinality insights into the network stack, much like what routers and switches report on like their flow exporters or SNMP exporters. We can do within eBPF space for applications and services inside of Kubernetes clusters or on bare metal with Mermin. And so that's really, it's pretty cool.
That unlocks some really powerful visibility that we just didn't have before.
Yeah, absolutely. Like for example, like one of the awesome use cases here is that if you have a Kubernetes cluster deployed on your own infrastructure or something like that, you wouldn't be able to tell which of the pods used which interfaces and what their route was through your physical infrastructure unless you had something like a network-oriented eBPF agent like Mermin deployed. But with it, you can, because we can actually see all the traffic across all the network interfaces, virtual or physical, and then tie it all together and create a real-time, high-fidelity picture for you of this pod talked to this pod, and it used these network interfaces to do that, and so it traveled through this switch. And then when you can marry that to the actual NetFlow data being produced by the routers and switches, now you can see the full path. And that's a really awesome, powerful use case for understanding how traffic moves, how your applications are communicating, and what type of things that you can do to improve their communication patterns.
Definitely. Not only that, but I would think like between teams too, right? Because being an open source tool, being o-tel native, having that flexibility to get that data into whatever platform you're using. So NetOps gets that visibility, DevOps gets to see it, try and maybe, at least put $1 in the buzzword jar, but bridge that gap between NetOps and DevOps a little bit.
Absolutely. And that was one of the main inspirations and purposes of why I wanted to create Mermin to begin with, was that I think the network space as a whole has been largely ignored by OpenTelemetry, unfortunately. There's been some efforts, but they've fallen flat. And I just think we could have done a better job. And so this is an attempt at doing a better job at exposing the important network telemetry related data inside of OpenTelemetry. And then hopefully that by bringing that data source into the OpenTelemetry ecosystem and world, that bridges the gap between where the observability data sets for NetOps and DevOps lives, and hopefully they can now share the same pane of glass to troubleshoot the same problems they're working on.
And that's so important, a collaboration across all fronts.
Yes, yeah, absolutely.
So now, time for my favorite segment of the podcast, hot takes. Sven, what is your hot take when it comes to eBPF?
So my hot take is that building a business around just an eBPF agent is going to be a really tough road. It's an incredibly powerful technology, but for one, eBPF requires you to open source your code base. Otherwise, you can't use it because of Linux licensing mechanism. And so you can't develop proprietary techniques within that. Anyone can just copy you, which is one problem. And so with that open nature, which is awesome for innovation and growth, it's going to be really hard for you to succeed as a startup, just basing your entire business model around your eBPF's agent capabilities. Startups that want to do that need to really focus on building an ecosystem around these eBPF agents to, and for one, protect themselves and create a moat that prevents others from entering their space of what they want to do. So differentiation for those companies, it has to be built on top of the eBPF agent, not just the agent itself. And so much so that my hot take number 2 is that eBPF is designed to work in a way where you could have many eBPF agents deployed on a single node, and it works just fine. But nobody really wants to manage configurations of then numerous pods. I would love to see the creation of one eBPF agent to rule them all. And so we need the ring of eBPF agents. And I think OB is trying to do that a little bit by donating it to OpenTelemetry, and they're really open to contributions from anyone. And so we'll see what happens. It'll be interesting to see if there's going to be a eBPF agent that combines the capabilities of OB and what it brings to APM, and what we bring to NPM, and what Falco brings to security. And ideally, I would love to see all 3 of those combined into one eBPF agent. So we'll see what happens. But if that happens, that means anyone else who is trying to build a eBPF agent that has their bespoke technique or logic in it should just be thinking about, how can I contribute this to the main players in the ecosystem, and then from that build my business model around the value I add on top of it, and not the value I'm creating inside the eBPF agent.
Exciting times that we're in. Well, Sven, thank you so much for joining us today. Now, Sven mentioned so many great links, not only our fandoms, but also the documentary, documentation. So we'll link all that in our show notes, so be sure to check that out. And we will see you next time on Signal Over Noise. Thanks for joining.
Take care. Bye.